Hi everyone, today I'm going to be doing the worked examples from exercise 7.4. So this is families of curves. So the first one here, they ask us to sketch a family of curves that have the derivative function of this for 0 to 2 pi. So the first thing we'll do is we will say, well, f of x is going to be the antiderivative of 2 cos 2x dx. And let's antiderive that. So the antiderivative of cos is sine, and we're dividing by 2. So 2 divided by 2 is 1. Oops, not cos, sine. So sine 2x plus c. So the purpose of them saying draw the family of curves is that, well, the family of curves consists of an infinite number of c values. So really, I mean, you're not going to draw too many. Maybe 3 or 4 would be enough. So from 0 to 2 pi, we can say, well, if c equals 0, it's f of x equals sine 2x. So let's draw that from 0 to 2 pi, and that's going to be 1 to neg 1 pi and 2 pi. So that's the first one. Now, I mean, we could say f of x, if c equals, let's do a different colour. Let's say if c equals 1. So that's going to be f of x equals sine 2x plus 1. Well, it's going to go up by 1 unit. So everything goes up by 1. So it will be like this. And let's just do one more for good luck. So let's say if c equals neg 1. So I mean, really you can do anything, but I'm just choosing 1 and negative 1 seem like quite easy values to do. So if c is neg 1, it's going to be going down by 1 unit. So this time, and we've got, so like that. So that would be a family of curves for when our derivative function is 2 cos 2x. So again, just note that it's talking about how, well, you don't know what the c value is, so you could have any value of c. So now they ask us to find the specific rule if f of pi equals 2. So, well, that's just where we have a point of pi and 2. So we can just sub that in. So f of x equals sine 2x plus c. So let's sub in 2 equals sine 2 pi plus c. There's 2 pi, the sign is 0. So 2 equals 0 plus c, c equals 2. So therefore, f of x will equal sine 2x plus 2. So that would be our specific rule. So let's move on. Find the equation of a curve that passes through the point 1, 0 if the gradient is given by this. So this is a pretty standard question. So our y, it's going to be a y function because that's dy dx, not f dash of x. That's going to be given by the antiderivative of 3x squared minus 2x plus 2 dx. So y equals x cubed minus x squared plus 2x plus c. So now that we've got that, we can find the value of c because they're giving us a point. So it's pretty straightforward. You just will now sub in the point. So 0 equals 1 cubed minus 1 squared plus 2 times 1 plus c. And 1 0, so 2 plus c. c equals neg 2. So therefore, y, not f of x, is going to equal x cubed minus x squared plus 2x minus 2. And that is our final answer for that one. Lastly, they're asking us to sketch a possible graph for y, and they're giving us, or y equals f of x, and they're giving us f dash of x. So what we need to do is really think about what each of these points mean in terms of the y graph. So here, this is where the gradient is 0. Gradient equals 0 on those points. So in terms of the y graph, they will be either a maximum, a minimum, or a point of inflection. So these will be stationary points, because stationary points exist when the gradient equals 0. So you might like to draw a little table. You don't have to, but it's quite a neat way of sort of analysing the graph. So we have our x values here, and at -1 and 1, and oh, that's a bit too big. So -1, 1, 3. So we know that at these points the gradient is 0. And then, well, that means that for our, what it looks like, well, the gradient is flat. So 0 gradient, so if you're walking on that, it would be a flat point there. So if we're before -1, so less than -1, you can see here is the gradient, and you've got to be careful because, well, the gradient of the gradient, you're walking up the hill, that's a positive gradient, but that's not what we need. We're trying to work out what the gradient value is, and we can see that the gradient value is below 0. This is a graph of the gradient function, so this is a negative gradient here. So it's going to be like this, and then between -1 and 1, this part here, it's above the x-axis, so the gradient is positive. So that means it's going to look like this, walking up the hill. And let's put that one there. And then between 1 and 3, well, this is negative. This is a negative section of the graph. So you've got to look at where the graph is. Where is it drawn, in the negative zone or the positive zone? So we're again negative. And then here, this is a positive section of the graph. So again, going up the hill. So the shape that we're going to get is going to be like this, like a W. And really, I mean, now it's just a matter of putting it on some axes. So this is x against f of x. And we don't know where those stationary points are going to exist, other than that we know what the x values are. So -1, 1, and 3. So let's say that's -1, 1, and 3. So look, I could put it here. I could put that here, and I could put that here. And I have a negative gradient, so walking down the hill. Then I have a positive gradient, walking up the hill. Then I have a negative gradient again, and then a positive gradient. So there's a W shape. And look, as I said, it could be anywhere. The Y value could be here. So we could have the graph that looks like this. Oh, that doesn't work, hold on. Could look like this. So wherever it is, we don't know, but we know the general shape, and we can know what x values are, what the x values are for the gradient of 0. So at those stationary points. So that is one method you could use to accurately draw a possible graph of f of x given a gradient function. And that completes the worked example.